All right. Good afternoon, everybody. Good morning. I see we've got a good number of folks trickling in here. So this is the first of a webinar series. We're going to do about 30 minutes here. We're going to give everybody about 2 minutes to get all settled in here. We've got a lot of folks, over 100 people registered here. So this is pretty exciting for the cold spray community coming together to have SPEE3D and Steve Camilleri kicking off the first of a webinar series here. So we'll, like I said, give it a couple minutes here to let everybody get settled in, but we'll do a few housekeeping items here first before we have Steve kick things off. So for those of you not familiar with the webinar function on Zoom here, you can see down at the bottom, there's going to be a Q&A section. Feel free to use that at any time to really reach out and issue any questions that we have. Steve's got about 20 minutes of slides here, and we'll have those questions at the end, and we'll go through them together. Obviously, if you have any specific items that you want to notify the team of, you can use the chat as needed. But we'll move along here pretty quickly. So a couple other housekeeping items. Like I said, this is the first of a webinar series. This is associated with the different sponsors of the Cold Spray Action Team and Large Scale Additive Action Team Conference. That event is going to be June 21, 22, and 23 in Worcester, Mass. Nicole, who's supporting on the tech side here, she'll share a link here in a minute to register for the CSAT and LSAT events if you guys haven't already. But essentially, this series is really to highlight some of the key players in the cold spray community doing some really amazing things. So we've got SPEE3D today, obviously. We've got VRC Metal Systems coming up in May. They will be on May 19th at 11 a.m. Eastern. So keep an eye out for that event as well. And then obviously the CSAT LSAT event coming up in June 21, 22, 23. It's going to be a great event. We've got hundreds of folks already registered. So if you're not registered, definitely do so, whether it's virtual or in person, because this event will fill up pretty quickly. There's a lot of interest, a lot of excitement. And of course, there's a baseball game at the end of the LSAT event. So how can you go wrong? Register for both if you haven't. We'd love to see you guys all there. This is going to be one of the biggest events for CSAT, just looking at a variety of different areas of interest, industry expertise. We've got power, we've got additive manufacturing. We have folks from heavy industry. We have folks from oil and gas, aerospace, defense, science and technology. So it's going to be a really exciting event. The LSAT event, we've got Dr. Aaron Weiss from the Navy Shipbuilding Industrial Base Task Force. He's going to pop in to talk about some of the supply chain challenges and what large-scale metal additive manufacturing can do for us. So I'm gonna turn it over to Dr. Vic Champagne, who is the Cold Spray Action Team Executive Director. He's going to say a few words here to kick us off, and then I'll introduce Steve Camilleri and SPEE3D, and we'll get things started here. So Vic, if you want to hop in with a few comments on the Cold Spray Action Team, we'd most appreciate it.
Thank you, Aaron. I'll be brief. I'm not known for that, but I will try. I'm excited this year about launching the large-scale additive action team. As we move forward, the future of cold spray is most certainly in the area of structural repair and 3D printing. And it's really exciting because 20 some odd years ago, when we first started down this road, people never even viewed cold spray as an additive manufacturing process. So we welcome Steve. They're leaders in 3D printing using cold spray, and we're all looking forward to hearing about all the exciting things that are being done in this area. So thank you all for attending this evening, this morning, wherever you are in the world, and certainly want to welcome you this year. Even though we're having a hybrid environment, we are unlimited in our face-to-face attendance at this year's CSAT. So thank you very much. Awesome.
Thank you, Vic. All right, so it is my distinct pleasure to introduce Steve Camilleri here from SPEE3D Metal Systems. I have to say, Steve, I think I saw you present the first time, maybe it was 2015, 2016 CSAT at Northeastern University. And we're talking to some of your materials engineers at the time, and you guys had kind of just rolled out the first version of the 3D printing system there. And it was really cool then. And now the things that you guys are doing, I mean, if you guys aren't familiar with Steve's background, I mean, Steve and Byron are both tech wizards here, and the system that they've come up with for printing, not only capable, but also flexible, versatile, and the things that they're printing, I think you guys were just at like a Formula One event. You guys have been out in the field making parts for the military. So there's a lot of really cool things that Steve and Byron and the whole SPEE3D team have done to really build up this technology. And I know the cold spray community is excited about it. The CSAT team's excited about it. So Steve, would love to have you chime in here and say a few words and talk to us about the latest and greatest and what you guys are up to.
Great, thanks, Aaron. Fantastic introduction. Yeah, hi everyone from Darwin, Australia, where it's currently 6 a.m. So yeah, good morning, good afternoon, good evening. I should be sharing the presentation now. Is that coming through? Let me get a thumbs up, Aaron. Yep, perfect.
Yep, you're good to go.
Excellent. So I'm just going to give a bit of an introduction and teaser today to what we're presenting at CSAT. So a lot of the really juicy stuff you'll need to come to CSAT to see. So let's get into it. So what does SPEE3D do? Well, we develop advanced manufacturing technology. So the product that you see on the screen there is a warp speed product. And really, this is all about solving supply chain problems. So cold spray is a fantastic way to do additive manufacturing. You can build parts quickly and you can build them very robustly. So I'll talk a little more about our product. So this is a little bit of a busy slide, but to put it very simply, our machines have a robot arm. You can see here at number 2, inside of a build chamber, which is all designed around powder safety, combustible material safety. And we also have a cold spray nozzle in the build chamber. We work with a variety of different metal powders. So traditionally, we work with aluminium and alloys, copper and copper alloys, and stainless steel. But I'll be talking about some enhancements to that later in this presentation. So the center of the whole process is our software, which allows us to take a CAD model and then automatically program the robot to build that part. And we also simulate the part as we go. So you'll get an SDL, a 3D mesh, talking about the actual cold spray geometry of the part before you even turn the machine on. So I've got a little video here of our process. So just before I get it started, that little hand on the end is partway through print. So the robot arm's extending up and to the right. The cold spray nozzle's at the bottom, it's stationary, the part moves and the nozzle is stationary. I'll get that started. So this is a real-time video building a little hand. So we all like this video because it looks like the robot's building itself a hand. So you can see that building up. There's the hand coming out at the end. So that toolpath was generated completely by our automation. So all we needed was the shape of the hand to generate that toolpath, and our software programmed the robot to make that part automatically. So lots of advantages to doing AM this way. So the process is quite rugged and transportable. I'll talk about that. The parts are very strong. Cold spray makes fantastic material. And it's also very high speed. So I'll give you some information about what we've been doing recently with defense. So here in Australia for the last 2 years, during the lockdown period, we haven't been able to travel. So Australia kind of got locked in, and we've really doubled down on working with defense in that time. So we've been out in the desert, the very high temperature and humidity and the dust. Australia is famous for its very, very kind of aggressive dust. And we've been taking our printers out into the field, literally dropping them on the ground and building parts for weeks at a time with Army and with Navy. So the top 2 images you can see here are from some of our Army work, and the bottom 2 are from our Navy work. So probably the most important thing that we've demonstrated, I think, other than the idea that we can make their parts, is that they can make their parts. So we've trained them to operate the process. We like to think our process is very accessible. And indeed, we've found that metalworkers and engineers from defence have been able to pick up the process and operate it very, very quickly and very easily. So I often get the question, where does the process most provide benefit? Or, what are you doing that's successful? So really, I have these three buckets of application that we talk about. So I would say everything that we've done has fit into one of these buckets: logistics, customization, or obsolescence. So the logistics bucket is the most obvious one. So this is the idea that rather than sourcing a part through a conventional supply chain, you're able to fabricate it yourself. So that gives you advantages, usually in time, but potentially in cost as well, or in quality. So most of the parts we've done fit into that bucket. Customization is a very interesting one. This one isn't obvious at first, but you'll often find, if you give an advanced tool to someone in defence who's used to making parts and solving problems, they will have a list in their head already of the kind of problems they want to address. So this might be just as simple as a guard around a rotating piece of machinery, or it could be a long-standing issue with reliability with one of their existing platforms. So in fact, people come into the process and engage with the training with immediate thoughts about where they'd like to apply the advanced tool. And customization has turned out to be a very interesting category. But yeah, generally it's maintenance issues, reliability issues, or safety issues that they want to address. So giving them the power to fix that is a real advantage. The last one's obsolescence. So there are defence platforms, at least in Australia, can last for 40 or even 50 years. So the idea that the original equipment manufacturers are around for that whole period and generating repair parts and spare parts usually isn't viable. So typically there are platforms that have a lot of outstanding part requirements that can't be met easily by industry. So the idea that defence can take charge of that themselves and generate their own parts to keep those platforms going is very valuable. So lastly, the concept of giving defence the capability to make their own stuff. In Australia, we refer to this as a sovereign manufacturing capability. So it's a way to get parts that doesn't require moving them across international borders. So Australia is very isolated. We're very good at having to solve our own problems very suddenly here. But, it's certainly at the moment, and over the last year in particular, the global supply chain has been failing us in a variety of different ways, and defence is no exception. So giving them the capability to solve those problems themselves is extremely powerful. So just referring to our Army work in particular, so we've really come off the back of two years of in-field exercises. So in the top center there, you can see that image is a aerial view of the configuration that we use out in the field for printing and machining and testing and heat treating parts. And that capability's proven to be extremely valuable. So I've got a short video here of some of the work that we did back in 2020. Unfortunately, the audio doesn't come through, but on our YouTube channel, you'll be able to see this video with the audio. So this fellow, Lieutenant Colonel Wright, was very quick in identifying where the technology might be applied. So in fact, he really pulled us out of the workshop and into the field very, very quickly. He foresaw that was the need that they had. So we work with a team of young Army craftspeople. So these guys were already qualified fitters. So they knew how to run lathes and mills and how to do basic heat treatments. And they were able to pick up the process very, very quickly. So in fact, I think that AM is going to be benefited once the world kind of realizes that advanced manufacturing is really just about tools, it's really about good quality computer controlled tools and equipment for giving leverage to these folks and not replacing them. So this is the hook loader process that Army use for moving equipment around. It's quite terrifying to see a printer up 5 meters in the air being unloaded, but one of these trials, the printer was moved, I think something like 10 times, and demonstrated how quickly they could set it up and get it going. So the printer was actually running while that huge cloud of dust was being ingested. It didn't miss a beat, which was good. So the tools, the software tools that are currently being deployed, we like to use Fusion 360 from Autodesk. We think that's a very good product for rapid workflows for AM, and plugs very nicely into our software. And it can be deployed in the field. So yeah, here's the heat treatment, here's the machining. So this is a reliability part for a fueling system. So again, the young craftsman was quite determined to do that particular case study. So yeah, that was us. The very first trial of the machine we took out was bright red, and that was very distracting for everyone. So another announcement we'd like to make today, we've developed a new cold spray deposition system, so a new nozzle. We've increased the amount of energy that nozzle can process. So what this means is it can shoot material faster. And what that means is it can work with a much wider variety of engineering alloys and materials. So for example, we're doing work now with titanium, tantalum, niobium, hard phase materials. And I'll be talking about the whole list when we get to CSAT. But if you're interested to talk to us about that product, we're happy to talk to people about that now. So let's talk a little bit about LSAT. So at SPEE3D, we're big fans of this idea of putting some energy behind a push into large-scale additive. So the key problem here is how do you make large parts with AM? So we're talking about parts that might be thousands of pounds, they might be 150 foot long. There's not really any existing solutions that solve those problems well. So if you're making one of these parts, if your need is for one of these parts, like a big ship's propeller, that's usually low volume. You don't particularly need 200 of those. You might need one of those, and you need it quickly, but typically the manufacturing lead time will be long, and you need it to be of high quality. But typically when you're making one part, with a process like pit casting, quality is very, very hard to maintain that low volume with that very manual oriented process. So it's quite normal to have a lot of rework on these parts, whether it's welding or, just machining. If you've just spent a week setting up your pit cast and it's come out with a crack in it, as a manufacturer, you're much more likely to weld that part and try and ship it anyway because of the effort required in getting that one part together. So it seems like additive is the perfect answer in terms of what additive does to this problem. And it's kind of interesting that humanity's got to here, focusing very hard on small parts, which have a variety of solutions, ways that those can be made. Whereas the large parts, which don't have that variety, we haven't particularly developed, a huge suite of very, very engaging AM solutions. So that's fascinating. So let me talk about one of the applications for large scale, so that's space. So here's my brave statement. The nation or nations that successfully colonize space will do so relying on practical advanced manufacturing. So it's actually not that brave a statement. Science fiction has known for a long time that this is a thing. So here's a cutout from a novella from 1945. But this constructor is both efficient and flexible. I feed magnetronic plastics, so that never got developed. The stuff they make houses and ships of nowadays into this moving arm. It makes drawings in the air, following drawings that scans with photocells. The plastic comes out at the end of the arm, hardens as it comes. This thing will start one end of a ship or a house and build it complete to the other end following drawings only. It's ready to make a spaceship hull now. I need one. Murray Leinster. So that paragraph is 80 years old. So you have to wonder how the original AM patents were granted, given that this concept predated them quite substantially. But science fiction is thinking about large-scale AM for space and has been for a long time, as I'm sure a lot of the science fiction fans in the audience will know. So let's talk about computer games for a moment. So I have these 3 images here. So this is from a game called Prey from 2017, quite recent. There's this thing called a fabricator. It's a large-scale AM machine, and really it's instrumental to the entire game. So it's a space station in space around the moon, and there are about a dozen of these things scattered throughout the levels of the game. So there's no debate in science fiction that large-scale AM is necessary in space because the supply chain just isn't there. So here's another example. It's a game called Astroneer. So you can see here a large-scale additive machine building a rocket. And you can see another game, Subnautica. This is a thing called the Mobile Vehicle Bay. So this is an aquatic game. This thing floats on the surface of the ocean and it makes your submarines a couple of flying drones. So, you know, very science fiction, but the point to make here is that large-scale additive is a quite human-friendly concept, and the idea of moving off our planet and taking our supply chain with us is not practical. So science fiction has had to invent these things to solve the problem. So let's get back to the real world for a second. So if we're talking about space being a prime example, so not only do we think that we need large scale to thrive in space, we actually need large scale AM to get us there. So the image here at the left is from 1950s era. That's a Werner von Braun with the Rocketdyne F1 engines from the Saturn V vehicle that got us to the moon. So you can see they're large. And on the right there, you can see a Rutherford engine by Rocket Lab, and you can see that's small. So that engine is really built to the maximum size that a laser powder bed fusion system will allow you to build a rocket engine. So that Rutherford engine. So there now are slightly larger laser powder bed fusion systems and experimental processes for making slightly larger engines. But in fact, the F1 engine, the concept of building something the size of an F1 engine is still science fiction. There are not additive processes, although people are endeavoring to create them. So we at SPEE3D agree large-scale additive is the way of the future. And we have an announcement coming at CSAT, so stay tuned for that. So that's the end of my presentation, and let's invite the Q&A. Thank you very much.
All right. Thank you, Steve. That was fabulous. So actually, I'll ask you to leave your last slide up there if you've got your contact info, just so people know how to reach out to you. And like we said at the beginning, folks, you can use the Q&A to add a question. We'll answer them here as we go. So first of all, Steve, fantastic job. You've really set us up here now. So everybody wants to come to CSAT to hear all of your great announcements, but now you've left us on a bit of a cliff here. So, you know, I don't know if I'll sleep tonight. One of the questions that came up here, really looking at some of your in the field type operations, you know, with all the sand, grit, everything that's going around. How do you do QA inspection? What kind of steps do you go through? What are maybe some of the tools that are involved?
Yeah, it's a great question. So it's a little interesting. I've always found it very interesting coming into additive, you know, over the last 10 years or so, that there almost seems to be this underlying avoidance of QA, this expectation that the equipment will take care of QA. But you know, engineering is not so. Engineers need to make sure the parts are right, the processes are right, that, you know, additive doesn't actually engage with that problem, especially that the existing processes and tools that people know still apply. So when we are working with the Army, so we've developed a process with them for in-field kind of validation and risk assessment and risk mitigation around the parts they produce in the field. So, you know, additive workflows make parts quickly, but if it takes 6 months to do the QA to get the part deployed like that, it doesn't help. The fast AM doesn't help. So what's the fast process for doing approval and validation and risk mitigation? So in the field where there's a high risk part to a certain risk category, parts are allowed to be made this way. So while the part is being printed, tensile bars are being printed as well. Those tensile bars get get machined and pulled in the field, destructively tested. So that validates the material. And we also load the parts into a thing we call a proof tester, where we add load and overload usually to the part. So if the risk category is high, you might add that load to destruction and understand what your factor of safety is. And if that load, if the risk isn't high, you might load the part to some level of overload, not destroy it, and then deploy the part. So it's all about closing out those risks. Additive doesn't guarantee that quality will be there. You've got to apply regular, old-fashioned engineering principles. You just got to do it quickly.
Speed is the key. Is that what I'm getting?
Yeah, that's right. So
right.
in the field, the difference between making a part in 2 days and making a part in 1 day can be huge.
Absolutely. Another kind of line of questioning here, looking at the hand that you printed, and it looks like there's a lot of interest in seeing that video if it's on YouTube. So if you have a link and you're able to share it, I know it looks like people would be interested. But there's interest in what's the kind of dimensional fidelity that you can hold with the system across maybe different materials, and what kind of performance do you get out of that system?
Yeah, so another very good question. So we've worked very hard on repeatability, on reproducibility of our process. So we can get multiple parts out of the process, and they'll measure out very, very similar to within tens of microns typically. And we will also be very close to the simulation. So not only can you see in advance what the part will look like, but you know that time and time again it'll come out looking like that. In terms of resolution, so this is really the trade-off with cold spray versus other processes. So, we're limited to the diameter, the bore of the cold spray nozzle in terms of the smallest feature we can generate. So that's about 6 millimeters in the case of our printers. And if you try and scale that down, you lose the rapid building advantage. So the kinds of parts that we address are typically the kinds of parts that might be cast normally. So, robust structural mechanical parts. And if you need to have finer detail than that, it gets machined in. So in the case of the defense work, 100% of the parts that get made are also machined. The machining workflows can be very short though, because you've effectively got a raw cast ready to go that just needs to be to have the precision added to it. So yeah, 6 millimeters is a minimum feature size because of the cold spray nozzle and machining to achieve better.
Got it. Very, very helpful. So as you're looking at some of the next generation capabilities that you're deploying, holding those types of tolerances, are you going to be able to continue that trend with the higher energy nozzles, and are you still going to use a lot of the same kind of core functionality for those, compressed air as a working gas, all that kind of stuff?
Yeah, that's right. So we've done a bit of work with nitrogen, less work with helium. We do most of our work with compressed air, and really that's just about build cost. So, we might be making an engine block over a day. A day's worth of helium, I don't even want to speculate what that might cost for 24 hours of spraying worth of helium. So even with helium recovery, where, 90% of the material gets reused, that's still a big logistical exercise to manage that length of spray with helium. So we've really focused on working with air. So there was a fantastic paper, I can't remember who presented it at last year's CSAT, where someone said, wow, we've compared nitrogen and air, and the material properties are actually very similar. So we've known this for a while, and air doesn't cost anything. It's recyclable, it's reusable. You're not going to drown anyone with air if we're putting a huge amount of nitrogen out. That's actually, you need to be careful to make sure that that nitrogen is expelled from where the people are. You don't want to be focusing many, many thousands of cubic feet of nitrogen into a room where people are working. So advantages to working with compressed air, I think, cost and safety being among those. And also Army and Navy, the concept of them bringing enormous nitrogen tanks with them out into the field, that doesn't work. So it's got to be something that can be sourced on the spot, and air is the one. So in terms of the new high energy nozzle, there's no sacrifice in reproducibility or in resolution with that. It'll do the same kinds of geometries that the existing nozzle does. And we're sticking with compressed air where possible to keep the cost down.
Got it. That's fantastic. So we're out of time here. There are still some more questions floating in. So if you did submit a question, we'll have Steve make sure that he pulls those together. And if you can't answer them via email, I promise he'll answer them at CSAT, and we'll all get off the cliff here at some point so that we can actually, hear your great announcements. I do want to just steal the screen for 1 second. Just a reminder to everybody, we do have the CSAT, LSAT events coming up. You can hear more from Steve, the SPEE3D team, as well as all of our other great speakers. So I want to really thank you, Steve, for taking the time this morning on your side to talk with us today and share some of the advancements that you guys are making. There's a tremendous amount of interest and excitement around this space. And I do want to encourage everybody to join us in a couple of weeks for the VRC Metal Systems webinar. It'll be the second in this series, again, highlighting great innovations in cold spray. If anybody is on the call and they're interested in engaging more in CSAT and LSAT, you can check out the website, www.coldsprayteam.com, and largescaleactionteam.com. We have some sponsorships available still. If anybody is interested in having their own webinar like this from the SPEE3D team, we do have some slots available. We'd love to have you. There's a lot of excitement in this community, and we are really excited to have you guys, Steve, continue to be a part of it. We're looking forward to the next webinar series. And if we don't see you at the webinar, we'll see you all June 21, 22, 23. So thank you all so much, Steve. Again, appreciate your time here. Do we have any closing words, Dr. Champagne, to wrap us up for the afternoon?
Yes, I do, actually. I was looking at the whole series of questions, and the questions came in regarding the availability of that equipment in the US, and it most definitely is. So it's not just something that is just acquired in Australia. There are a number of systems in the US already, and they're being tested. And another question was the video. The video is on YouTube, the question came up about fidelity. It has pretty good fidelity, and fidelity is also influenced by the feedstock powders too. So with that, I thank you, Steve. Very informative, eye-opening for those that just think cold spray is a coatings process, and it's been a long and winding road, but we're getting there. And again, the future is definitely 3D printing. Hope to see everyone at CSAT and LSAT this year. And just want to wish everyone good evening, good afternoon, good morning. Thank you.
Fabulous. Thank you, everybody. Have a wonderful afternoon.